Right, in this video we're going to look at potential dividers in terms of the components we're going to put in them to make them be sensing circuits. So two of the components that we deal with regularly are LDRs. An LDR acts by, when you increase the light intensity, you decrease the resistance. Okay, so when you increase the light intensity, you decrease the resistance. The other component that's very important is the thermistor. Okay, so both of these are type of resistors. Now, this one reacts to heat. Now, the interesting thing about when you increase the heat of a thermistor is it does the opposite to something you've already learned. When we were talking about filament lamps, we were talking about wires heating up. When wires heat up, the resistance goes up. However, in a thermistor, that is not the case. The thermistor does the opposite, the resistance drops. So you just need to remember that in every case, whenever the sensing factor increases, the resistance will decrease with both of these components. So, having said that, let's throw these into a circuit and let's discuss some of the concepts surrounding them. So we'll start off with an LDR. So here we are, we've got a fixed resistor, I'll label that FR, and then we've got our LDR, which is represented by that symbol there. Okay, so that's LDR, and we're going to put a voltmeter across there. Now our sole purpose is to observe what's going to happen across this fixed resistor in this case, when I do something to the LDR. So let's do something to the LDR. Let's increase the light intensity. So we're going to increase the light intensity. As we've already suggested, what would we expect to happen to the LDR's resistance? Well, we would expect the LDR's resistance to go down. So the LDR's resistance goes down. What does that mean happens to the voltage across the fixed resistor? Well, that means that the voltage across the fixed resistor will go up. Why will it go up? Well, it's to do with this idea about the ratio of the resistances. Okay? The ratio of these resistances, it's gotten bigger or more in favour of the fixed resistor because this resistance has dropped. The fixed resistor is relatively bigger because this has dropped, and therefore the voltage across the fixed resistor increases. So let's write that down. So because the ratio of resistances shifts in favour of the fixed resistor, that then means that the voltage across the fixed resistor will increase. Now, on a side note to that is the common explanation about what happens when we increase the light intensity on my LDR. Ratio resistance is shift in favour of the fixed resistor, and therefore we're going to have a greater voltage or PD out across the fixed resistor. As a byproduct, lots of students like to talk about the current in these circuits. Now, as a result of this, what's going to happen to the current? The current in this circuit is going to do something. Well, if the resistance of this has gone down and this has stayed the same, what does that mean about the current? Well, that means the current is going to go up. Why is the current going to go up? Well, because the circuit's whole resistance has dropped. Yeah, fair enough, this has stayed the same, but this has dropped. That means the current in this circuit here is going to drop overall. We already kind of suggested that with in the previous video, but now we're applying it to the situation. One thing you need to be aware of is that this is not the reason for this. Okay?
This is not the reason for this. The fact that the current goes up does not mean that the voltage will go up. Okay? The current is the same in both of these. The fact that the relative resistance of this resistor has gone up, it hasn't actually gone up, but the ratio has been moved in favour of it, so it's like it's gone up, and so the voltage and the PD across it will increase as well. The greater the resistance, the greater the PD you're going to have across it in a circuit of that nature. Okay, right, so one other interesting point that we might want to raise is what happens to the voltage across the LDR when we increase the resistance? Oh, sorry, when we increase the light intensity. Well, if we increase the light intensity, the resistance drops, the voltage across the fixed resistor increases, so therefore we'd expect the voltage across the LDR to drop with the resistance as well. Funnily enough, it should drop by the same proportion to which the fixed resistor has increased, hence potential divider circuit. Right, let's look at the thermistor then. We're going to put the thermistor in a different position. Okay, so the thermistor, we're going to put in there with a fixed resistor. So, thermistor, fixed resistor. And this time we're going to put my voltmeter across my thermistor. So, how would we describe this when the temperature of this drops? Well, if the temperature drops, that means the thermistor is going to always act in opposition, and so we would expect the resistance to increase. If the resistance of this increases, what would we say happens? Well, the ratio shifts in favour of the thermistor. What does that mean in terms of the voltage? Well, that means that the voltage across that thermistor would increase. Again, as a byproduct, what happens to the current? Well, if the heat is decreased, that means the resistance is increased, the fixed resistor stays the same, that means that the current is going to drop. Remember, because they act in opposition as well. Remember, I'll say it again, the current changing in the circuit is not the reason for the voltage change. The reason for the voltage change across that thermistor is to do with the fact that the thermistor's resistance has changed. Okay? Right. So, finally, the side issue. If the fixed resistor is there, we don't know what the voltage is across it, but we can say that if the voltage across this resistor has increased, therefore we would have expected the voltage across the fixed resistor to drop with the increase in the voltage across the thermistor. So, it's all to do with the relative sizes of the resistances to each other. A very high resistance will take a very large proportion of the PD, of the EMF, as opposed to a smaller resistor or a relatively smaller resistor in the same circuit. So it's all about the relative sizes of the resistors in the circuit as to how much voltage each is going to take. The larger the resistor, the larger the chunk of the voltage it's going to take.